Hello everyone, I'm Donald Murphy, Marketing Manager for NVIDIA's GPU Technology Conference, otherwise known as GTC, and I want to welcome everyone to GTC Express. GTC Express is a year-round extension of the great content available at GTC, providing insight and unique perspectives on GPU computing from top scientists, researchers, developers, and industry practitioners. So I encourage you to come back often and participate. It's my pleasure today to introduce my colleague Shalini Gupta, Senior Research Scientist in the Mobile Visual Computing Lab at NVIDIA Research, where she designs computer vision algorithms and solutions for mobile platforms and GPUs. Previous to working at NVIDIA, Shalini was an imaging and architecture scientist at Texas Instruments. She received her master's and doctoral degrees in electrical and computer engineering from the University of Texas at Austin, and a bachelor's degree in electronics and electrical communication engineering from Punjab Engineering College in India. She has numerous publications in peer-reviewed computer vision journals and conferences, and is also a reviewer for several image processing and computer vision journals. Today, Shalini presents OpenCV, accelerated computer vision using GPUs. She is joined by Frank Brill and Shervin Amami, software engineers here at NVIDIA, who will be helping with the Q&A. So you're welcome to submit your questions at any point during the presentation by typing them in the area provided on your screen. We will be recording this webinar and making it available for download on the GTC website in the next week or so. But first, I want to introduce my colleague Julia Levitas, Senior Product Manager in the Tesla Group here at NVIDIA, who's going to talk about GPU Test Drive. So with that, welcome Julia.
Thank you, Donald. So I would like just to go through a few steps to give a little quick announcement in the very beginning before we get going and dive deeper into OpenCV itself. First item, I want to give you introduction on our GPU access. So today, Shalini will be presenting OpenCV with GPUs, how it's going to be accelerated on GPUs. For everyone who attended this webinar, we will provide GPU access on our NVIDIA cluster. In order to get access to NVIDIA cluster, please email me at jlevitas@nvidia.com, put subject line OpenCV GPU Test Drive, and please add your name and phone number. This information will be required to connect to you to give all the instructions how to access the cluster. We're also looking for your feedback. We're working on more OpenCV related webinars and would like to make sure that we cover all information you are interested in and improve whatever we did not do perfectly right today. So looking forward for your feedback, and in the pipeline we have 2 more webinars for OpenCV, one that will be more technical than the one we present today with more hands-on and information about how to develop with OpenCV, and another one we have Intuvision. It's a software provider for video analytics. They use OpenCV for their software, and they will be presenting their solution and how they developed it using OpenCV in July. Also, just a reminder that if you want to cover more questions on OpenCV and GPUs, there is a great Yahoo group, and I believe most of you are already familiar with that. But check it out if you have more questions about OpenCV. And also, there is a sign-up link for more webinars. So if you're interested in more webinars on topics, OpenCV and any other topics that NVIDIA presents, so feel free to sign up for it. Without further ado, I would like to hand it over to Shalini to go over OpenCV. Thanks.
All right. Thank you, Julia and Donald. So hello, everybody. I'm Shalini from NVIDIA. And these are the topics that I'm going to cover today. I'm going to tell you briefly about what the OpenCV library is, and then I'll talk about why we're interested in using GPUs and porting OpenCV to GPUs. Then I'll walk you through a small example, a computer vision example of running some filters on an image, both on the CPU as well as using the CUDA version of OpenCV. Then I'll briefly introduce you to some of the functions that exist in the CUDA port of OpenCV. Then I'll discuss some advantages and disadvantages of both the CPU and the CUDA versions of OpenCV, and generally of using GPUs for computer vision. I'll talk a little bit about what's to come in the future with regards to GPUs and OpenCV, and then lastly I'll summarize the main points of this talk. So what is OpenCV? So if those of you who are not familiar, it's a large open source library. In fact, it's one of the most comprehensive collections of computer vision image processing and machine learning functions that exists. And it's distributed under a fairly permissible BSD license. The source code is available and it's free to download, and you can download it from opencv.org and build it yourself. And the really cool thing about it is that it's been around for a long time, 14 years now, and it exists. The OpenCV can be compiled for various different platforms, including x86, the ARM CPU, as well as CUDA enabled GPUs. And for many years, for 11 years, the main API for OpenCV was in C. Recently, since the past 3 years, it's been ported to C++, and it's also an expanded API. And there also exist Python and Java bindings for it. And it runs on the Windows operating system, OS X, Linux for desktop, and for mobile it runs on Android and iOS, and also recently for Linux on ARM. So as a developer, it's really cool because there's so many different platforms on which you can compile your code. If you write a function once, you can just take the same code and cross-compile it for different platforms and be able to publish it across the various ecosystems. So, like I mentioned, it's been around for a long time. It's been downloaded over 6 million times. It has a very strong user group online community of over 47,000 users. Many companies have used it in their products and for many different varied applications, ranging from stitching street view images to automated inspection and surveillance, for robotic and driverless navigation and medical image analysis, in video and image searching and retrieval of content. It's used in 3D structure for motion in movies, and in interactive art installations in museums. So like I briefly mentioned, there exist ports of OpenCV for various different hardware platforms and CPUs. So among the desktops, OpenCV originally was written for the single-core x86 CPU, and actually OpenCV first started as a project at Intel, and so hence it was first written for the x86 platform. And from there, it has now evolved on as an independent software project, which is now managed by a company in Russia called itsys.com. And the current version is 2.4.5, which contains over 2,500 functions with multiple options for each algorithm, and also many algorithms operating on different types of data, ranging from 8 bits to 16 bits, single channel or multi-channel data. Also, there exists a port of OpenCV for the CUDA-capable GPUs, which was a project which was sponsored by NVIDIA about 3 years ago. And this port contains about 250 functions, most of which are the very commonly used functions, and they give about 5x to 100x speed up in comparison to a single-core CPU. There also exists a smaller port of the library containing about 100 functions, which runs on OpenCL. capable GPUs. And however, note that it's been observed that the launch times for the OpenCL versions is about 7x slower than that for the CUDA version that runs on the GPUs. Also recently, I think this was about 3 years ago in 2010, there was a port of OpenCV to the Android operating system to run on ARM. And this is the Android OpenCV for Android is not optimized. However, there's also available a OpenCV for Tegra platform, specifically for NVIDIA's Tegra mobile platform, which contains about 50 very commonly used functions which are optimized using the Neon SIMD in the ARM CPU, as well as some GLSL optimizations, as well as some multi-core optimizations for the quad-core ARM CPU. And it gives about 1.6 to 32x speed up in comparison to the OpenCV for Android version. So, like I mentioned, it's a library for computer vision and image processing functions, and it contains a myriad different scope of functions ranging from your image and video input and output functions and simple processing and display. And the OpenCV modules that cover these are the core, the image proc, and the high GUI. So these are all helpful for you to load videos and images and display them on your display to see what the results look like. There's also modules for object and feature detection. There's modules for doing geometry based or stereo computer vision, and recently there have been modules added for computational photography. There's modules for machine learning and clustering, which contains all your pattern classifiers as well as some a number of clustering techniques. And then, like I mentioned, there's also modules for GPU that are in CUDA as well as OpenCL. Okay, so why are we interested in using GPUs for computer vision and image processing? So if you sort of look at the history, for 50 years the CPUs kept on increasing in performance and power, and they drove a lot of the innovation, technological innovation. However, they've sort of reached a point where they've reached their speed and thermal power limits, and at this point most of the improvements in the CPUs have been mostly incremental in memory caches or in small complex changes to the architecture. The other thing that's sort of major in the CPU world that's happening is that the introduction of multiple cores. However, when you do introduce multiple cores, there's often the burden that the software programmers have to explicitly write their code to be able to make use of these multiple cores using multi-threading, TBB, or pthreads, or any kind of threading software libraries. However, this is quite burdensome, and not a lot of software code exists that's actually multi-core. GPUs, on the other hand, have recently been developing, and they've very rapidly been developing. And the idea for the GPUs is that instead of having more complex cores, you have many hundreds of smaller, simpler cores on which you can do in parallel a number of jobs together. And they're fairly easy to extend or make more powerful simply by duplicating or increasing the number of the simple cores. And unlike the CPUs that are sort of reaching their limits of performance, GPUs continue to grow exponentially, and there's continuous innovations, and I'll talk some more about that further. So if you look at both the gigaflops as well as the bandwidth for GPUs, you see that GPUs have exceeded CPUs both in terms of memory bandwidth and as well as in terms of the compute capabilities. And the other motivation to use GPUs specifically for tasks of image processing and computer vision is that, in some sense, GPUs that were traditionally used for graphics, in graphics you have a physical representation of your world, and in terms of where the objects are in the scene and so on and how they're lit up, and then you try to create a video or a 3D a 3D video or an image that represents that world. In computer vision, in some sense, it's pretty much the dual of the graphics problem, in the sense that in computer vision we have video or visual input in terms of video or images, and the task that we're trying to do is we're trying to interpret or create a representation of our world in terms of what objects are present and what their position is, and so on. So, and the one thing that both these tasks share in common is that many of the problems in computer vision, just like graphics, are massively parallel in the sense that they involve applying the same operation over and over to a large set of pixels, and hence it makes computer vision tasks very easy and very portable to GPUs. So now I'm going to introduce you to a simple example of how you would write a CPU function using OpenCV, as well as its GPU counterpart using the CUDA port of OpenCV. Okay. So I'm going to walk you through this very simple this is a C++ example. And the main things that you want to do is, first of all, you want to include the appropriate OpenCV libraries. So in our case, this is OpenCV2, OpenCV.hpp. This is the main OpenCV library that you want to include, which basically includes all the other header files that you might need. Then you can include a namespace CV, or you can omit this if you prefer to instead append CV : to all the OpenCV functions that are noted here in green. So the first thing that we're doing here is we're using this functional imread, which is part of the OpenCV image processing library. And here we have a JPEG containing an image of a car, and we're reading that into an OpenCV structure mat. And we've called this mat variable as src. And so once we've loaded it successfully, we make sure that we've successfully loaded it. We also create a mat, which is the mat. I just want to point out is the basic founding structure of OpenCV. So every image is represented as a mat, a single channel or a multi-channel mat, and is very often used in OpenCV. So here we've created a destination mat where we'd like to store the result of whatever processing we do on this image. Then we apply a bilateral filter to smooth this image and at the same time preserve its edges. And then we apply a canny edge detector to basically detect all the sharp edges in the image. And then we use the imWrite function to write out this image to an out.png, which we can to our file system, which we can later read. So this is our input, and after the series of steps of applying the bilateral filter and the canny edge detector, this is what our output would look like. So let's look at how this the simple program would change if you wanted to use the CUDA GPU module of OpenCV to pretty much do the same task. So in addition to including the OpenCV.hpp header file, you would also include, in this case, the GPU.hpp header file. So that's the first change. The other changes to note is that you would load your image using imread, pretty much like the previous example, into a src mat which resides on the CPU memory. However, now what you have to do is that you have to explicitly transfer this mat that resides on the CPU memory over to the GPU memory. And in order to do that, you would first instantiate a GPU mat and upload this src that's sitting on your source explicitly to your GPU mat. Then you would also create on your GPU memory a space for storing the result of your GPU. And then So note here that you're using the GPU namespace here to differentiate the GPU functions from the CPU functions. And then you would do the processing using the bilateral filter on the GPU. Again, you would apply the canny on the GPU. And then you would basically download the result to a destination mat which is residing on the CPU from your GPU mat. So again, the result is identical, and this is what it would look like after you've applied the canny edge detector. And so looking at both these functions, you can see that you had to make very minimal changes to your code that you had written for the CPU to port it over to the GPU CUDA module. And you can see that it mainly just requires the user to include the right header files, as well as a step of transferring the data from the CPU to the GPU, calling the right functions on the GPU, and then transferring the data back. So this data transfer does require some time, and I benchmarked, for example, for this particular example, I benchmarked on my desktop GPU, which had an i7 8-core i7 CPU, x86 CPU, and it also had actually a pretty small GPU, which was I'm sorry, I hear some disturbance. Could everybody mute their mics? Thank you. Yes? Okay. Anyways, I'll continue. So you can see that it takes about 0.5 milliseconds to transfer the memory from the CPU to the GPU. And furthermore, there's a significant improvement in the performance of the bilateral filter, from almost more than 10x improvement in performance in going from the CPU to the GPU. And a small improvement in the canny edge detector, but not too much, and I'll discuss why that is the case a little bit more. And overall, with just a few changes to your program, it resulted in about 12.7x speed up on my desktop Linux system. Okay, so now I'd like to switch gears and introduce you provide you with just an overview of some of the functionality that's available in the CUDA port of OpenCV. And again, this is a pretty high level this is a very high-level overview, and I would encourage you to go to the actual web links and check out details of these functions yourself, and the web links are also provided towards the end of this section. Okay, so the GPU CUDA module includes your basic matrix operations like addition, subtraction, division, square root, and all of these apply to matrices. They also include things like matrix multiplication and some interesting features for manipulating if you have multi-channel matrices, so you can merge, for example, two matrices of the same size to create a multi-channel matrix, or split a multi-channel matrix into its constituent channels. So for example, here this is an example where you can convert an RGB image to the hue, saturation, and value space, in which case it would have three color channels of hue HSV, and then you can split all three of them and for example, work on individual ones or see the results. There's also operations available to apply geometric operations on the images or matrices, which include, for example, resizing of images, rotating of images, and also warping using warp perspective or warp affine. And For example, the warp, perspective, and affine are often, these are functions that are often used, for example, in panoramic stitching, where you would want to first compute the affine transformation between two images such that they line up, and then they would be appropriately warped and then stitched together. There are other geometric and other mathematical operations available on images as well. For example, it does provide the ability to compute integral images and square of integral images. And if you're familiar with computer vision algorithms, integral images are an efficient way to compute sums of rectangular regions in images, and they're extremely useful for object detection as well as recognition, as well as for feature tracking. So they help to optimize computing HAR-like features that are often used in object detection. And it also allows there's also functionality built into the CUDA module to allow you to apply your own geometric transformations using your own custom functions. For example, you might have a lens with a significant amount of geometric distortion, and you might compute the distortion or calibrate your distortion offline, and you might want to apply your own custom function to correct this distortion. There's also other basic image processing functions available, for example, functions for image smoothing, which include blur, box filter, or Gaussian blur. There's functions for applying morphological filters, including dilate, erode. And then there's functions for standard edge detectors that are Sobel, Scar, Laplacian, or Canny. You can also apply your own custom 2D filters by specifying the coefficients yourself, both for separable filters as well as non-separable 2D filters. And there's also functions available for color space conversions on the GPU. Then some of the other image processing functions that are available are for image blending, blending of two images. You can also do template matching, which is if you have a template of an object that you're searching for an image, then you can basically, using various numerical metrics, it could be cross-correlation or other metrics, you could try to find that template and in your image, and this is oftentimes used, for example, in industrial automated inspection. You can also compute Gaussian pyramids, and they're often used in scale invariant feature and object detection. You can compute image histograms, as well as there's a function available for equalizing the histogram to enhance the contrast of images. So here you can see the histogram of this image here, and you can also see the contrast enhanced version of this image after applying histogram equalization. Then there's image denoising functions. There's both the bilateral filter, which is edge preserving, smoothing, as well as the fast non-local means denoising that's available in the CUDA version. There's also the standard functions for computing the Fourier transform of an image. You can also convolve your image with the filter of your choice, and then you can manipulate the Fourier spectrums. You can multiply and scale the spectrums, etc. There's also functions available for mean shift filtering as well as mean shift segmentation. Then there's functions available for shape detection, for example, using Huff lines or Huff circle and Huff line functions, and these are very useful. For example, the Huff lines function is pretty useful, for example, for detecting straight lines, for lane detection in automotive vision, as well as detecting straight lines in buildings, or for perspective correction. And circle detection has applications in cell or coins or ball detection or any kind of elliptical or circular objects. There's also the CUDA object detection module that includes the HAR and LBP cascaded adaptive boosting classifiers, which can be used for face, human face detection or for detecting facial features. There's also a object detector based on histogram of gradients. That's the HOG feature detector, and that's useful more for detecting, for delineating objects that are delineated by their shape as opposed to their texture, which is the case for the HAR and LBP classifiers. And the HOG detector is often useful for detecting persons or pedestrians, cars or fruits or hands, any objects that are delineated by their shape. And then there's also the standard interest point detectors like your Harris and SURF and FAST, ORB, or good features. And there's also techniques, functions available for matching these features. Again, so after matching for example, two sets of interest points in two images, you might also want to compute the 3D structure or pose of an object in the scene using, there's a function, there's the standard RANSAC algorithm available for that. There's also functions available for doing dense stereo correspondences between a left-right pair of images to compute the disparity, as well as different functions for representing the disparity as 3D maps or color in terms of 2D color images, as is shown here. There's also functions available for sparse and dense optical flow, and this again has various applications in motion estimation and object tracking, as well as in image interpolation. And then there's also functions available for foreground and background segmentation. So as you can see here, this was helpful in removing this object here by detecting this foreground object. And then lastly, what I wanted to mention is that in the CPU version of OpenCV, it provides you access to the actual image data, or it provides you a pointer to all the image pixel data, which enables users to write their own custom code on the CPU if a certain function that they're looking for is not available in OpenCV. Similarly, the GPU accelerated version of OpenCV also provides the user access to the GPU memory or the pixel data such that they can write their own CUDA kernels. And obviously there is some it does require some knowledge of understanding CUDA and how to program in CUDA, but there is the ability for users to do that. And like I pointed out, this was just a brief overview of some of the functionality available in the CUDA module of OpenCV, but if you'd like to find out more details, I encourage you to follow this link and check out the very detailed documentation maintained by the folks at itsys.com, and find out more about how to use the various functions in the GPU module. So moving on, I'd like to kind of discuss some of the pros and cons of using the GPU versus the CPU version of OpenCV. So some of the advantages of using the CUDA module of OpenCV, that like we saw from that example, the code, the GPU code is very similar to the CPU code. So if you're familiar with writing OpenCV code in CPU, it's fairly easy for you to switch from the CPU to the GPU, because it essentially has the functions have pretty much the same API other than appending a GPU : to the front of the functions. And the other advantage is that there are certain OpenCV or computer vision functions that are very, very parallel, inherently very parallel in the sense that they require applying the same operation over and over to many different pixels in the image. So the CUDA module tends to be really good for such functions that are highly parallelizable and do not have, and they consist of long parallel operations and do not have as much data transfer back and forth between the CPU and the GPU. and such functions also tend to run the slowest on the CPU that have very long compute on each pixel, so they tend to port very well to the GPU. So its example of such a function is, for example, the bilateral filter that we saw before, which resulted in over 10x speed up on the GPU. And this fact also helps because the fact that we have this CUDA module available for OpenCV has now enabled a lot of the tasks that were compute bound on the CPU. It's possible to do them in real time. For example, stereo vision or pedestrian detection or dense optical flow. These types of functions can be done in real time using the CUDA module now. And the other thing to note is that in the future, we can envision that there could be a way to, for example, in fact, currently there is a way to check if the GPU is indeed available on your system, and the GPU accelerated version of OpenCV can be enabled at runtime. However, in the future, if a user can maintain a table of the different performances between the CPU version or the GPU version, then the functions can also be enabled at runtime based on whichever function runs faster. There are some disadvantages to the CUDA module as well. One of them being the fact that obviously the API for the CUDA module of OpenCV is not as extensive as the CPU version, which the CPU version contains almost 10x the number of functions in comparison to the CUDA module. However, we are continuously at NVIDIA investing and growing this part of the library. The other limitation is that oftentimes not all data types that are available for the various functions on the CPU are actually available on the GPU. The other thing to note is that you have to explicitly program for CUDA and invoke, write slightly different code to invoke the CUDA modules. You also have to, as a user or programmer, have to handle data transfers explicitly between the CPU and GPU yourself. And currently, the CUDA module only runs on the NVIDIA GPUs that are CUDA capable. And some operations in computer vision, for example, the canny detector we saw previously, doesn't actually speed up very much on the GPU. And I'll discuss a little bit more about why we see that. And the last thing to note is that when you first invoke your very first CUDA kernel, there is a startup delay. And I'll talk a little bit more about this in detail. So like I mentioned, so what happens is that if you, for example, you're processing a video sequence, then the very first frame that you process on the GPU, your CUDA has to be initialized. This results in about a 2-second delay for the very first frame. However, after that, the delay is about just 1 millisecond. And so if you have functions where you're just going to call, say, a single image on the GPU, you might experience this delay. However, if you're processing video frames, the CUDA module is good in that you would only experience this delay for the very first frame, and the subsequent frames would not have this startup delay. And then I want to talk some more about the serial functions that I mentioned previously that actually don't port very well to parallel architectures. And an example of that was the canny edge detector. So for such functions that are somewhat inherently serial in nature, and they're just by their design are hard to port to a parallel architecture, there's some hope for those as well, in the sense that oftentimes if you look around in the literature is continuously evolving, and there exists CUDA parallel algorithmic implementations or equivalent implementations in CUDA for those serial algorithms that can help. And there's actually some very good courses, open source courses now on Audacity as well as Coursera that if you'd like to learn more about these efficient CUDA parallel algorithms, you can go to and check out these courses as well. The other case can be sometimes it might just be more beneficial to run the serial version of the algorithm on the GPU, even though you don't really get much speed up from it by running it on the GPU, just to be able to save some time of transferring memory back and forth between the CPU and GPU. And like I said, this field of porting computer vision algorithms to parallel architectures is very rapidly evolving, and there's a lot of research that's being done continuously. And also, as the new generations of GPUs, GPU hardware, as well as the CUDA drivers evolve, more and more algorithms become available on the GPU architecture, and more computer vision algorithms can be ported over efficiently. There's one other thing to note about the GPU memory. So basically you can have two kinds of GPUs. You can have a dedicated GPU, which is often, or a discrete GPU, which is often connected to your system via a PCIe Express, or you could have an integrated GPU, and oftentimes the discrete GPUs are, an example of that could be in your desktop or workstation, and an integrated GPU is for example could be in your laptops. And there's some pros and cons to how you would access the memory on both of these. So in the case of the discrete or dedicated GPUs, they have their own high-speed memory, whereas in the case of the integrated GPUs, they share the CPU's slower memory. And in the case of the discrete GPUs, you would have to explicitly transfer memory from the CPU memory to, transfer data from your CPU memory to your GPU memory. But in the case of integrated GPUs, since they're all sort of sharing the same memory space, the transfers are very fast and almost free. Like I mentioned, in the case of the dedicated GPUs, you have higher memory bandwidth, and in case of the integrated GPU, since they share the memory with the CPU, it's usually slower and of lower bandwidth. So for these two different types of architectures, you would want to port different functions onto it. So for the case where you're using a discrete GPU, you probably want to port over functions that have a lot of long compute chains, such that you don't have to transfer too much memory back and forth. Whereas in the case of the integrated GPU, you could probably do with functions that have, you could run functions on the GPU that have little processing. So what's in the future with regards to OpenCV on the GPUs or CUDA? So one of the things that NVIDIA recently announced is our a very new mobile Logan chip, which is going to be the very first mobile chip with a CUDA-capable GPU on board. And so it will be possible to actually run OpenCV CUDA functions on a mobile device for the very first time. And you should watch out for this chip coming out, because it's likely to come out pretty soon. And so this is a great platform, especially for low power and low area, the kind of applications that require low power and low area, for example, automotive and the mobile space. And currently, this chip is actually not available for purchase. However, we have these development platforms that NVIDIA has made available called Kayla and Jetson. They contain a Tegra 3 mobile system on chip with a discrete GPU, which is often contains about 192 or 384 microprocessors. And so you can buy this system, although it's a discrete GPU, but it can act as a proxy for prototyping before the Logan chip is actually launched. And in addition to, so if you were to experiment with the Kayla or the Jetson platform, in addition to the CUDA-capable OpenCV parts, you will also be able to get the Tegra optimizations that we provide, which is on Neon or GLES code, or using some multi-threading on the ARM processor. And lastly, I just want to point out that in the future, more and more CUDA optimization will be added to OpenCV and it's also harder to program Neon as well as using GLES, but hopefully it'll be easier to program with the OpenCV for CUDA library. There's also an initiative that is going on at the Chronos standardization body, the body that has over the years standardized OpenGL, OpenCL, and OpenVG standards. And the standard is called OpenVX, and this is a new standard for hardware accelerated CV. And there's a number of key participants in this standard, and if you have any particular questions about that, both Sherwin and Frank are very active from NVIDIA at this standardization, and you can particularly ask them. So one of the goals of this standardization endeavor is to try to have a fixed model for being able to optimize computer vision functions across different hardwares from different vendors and on different platforms. And one of the cool things about this model is that it uses a graph model versus a synchronous programming model, and the idea being that the programmer is going to basically put together a graph of the various steps that they want to perform in their image processing or computer vision pipeline, and then it would be up to the implementation underneath to pick the right hardware and the right software and things like that to basically create the most optimal implementation for that particular platform. And so, just to summarize, OpenCV is a great library. It's a very large, comprehensive library of a large number of functions, and it has been around for a long time. It works on many different platforms, so and it's distributed under a good BSD license that can be used by both the academic community as well as in industry for writing production code. And off late, GPUs are pretty much growing much faster than CPUs, and they're the future. And the cool thing about the GPUs is that, and image processing and computer vision, is that many CV and image processing algorithms are great for GPUs in that they do the same task over and over, and so they're highly parallelizable. And so NVIDIA provides this OpenCV for CUDA module that we've invested in recently, which contains about 250 functions, and also provides the ability to write your own custom CUDA kernels on the GPU, and encourage you to go out and check out the OpenCV for CUDA module more. And there's more to come beyond the OpenCV for CUDA with the OpenVX standard to extend it to other hardware platforms, including DSPs and fixed function hardware. And we really believe that GPUs are the future, and GPUs are going to be in everything. So they're going to be in everything from a Tegra tablet or a smartphone or a Shield device to your development boards, to desktop PCs, and to cloud computing and supercomputing centers. So GPUs are really the future. So I would highly encourage you to check out the OpenCV for GPU module that we provide, and try it out. So with that, I'll hand it over to Julia to talk some more.
Thanks, Shalini. And thanks a lot. I already got a few responses, requests to access our GPU cluster. Thanks a lot for that. And just a reminder for those who missed the first slide, if you want to test out OpenCV with GPUs, you can request access to our cluster. In order to do so, send email to me at jlevitas@nvidia.com with subject line OpenCV GPU test drive, add your name and phone number, and I will reply to you with instructions how to log in. Also, we're looking for feedback about the webinar, and we're planning to have more webinars in OpenCV. Just a reminder, don't forget to submit your survey. We will have a Tesla board for those who submitted their survey. Also, if you have more questions, refer to Yahoo group, and you can register for more webinars, and here's the link for that. Thank you, and then I will hand it over back to Donald to, oh, we have questions first, right? So now we'll have some time for questions. Thanks.
Hi, Shalini. This is Frank. Can you hear me okay?
Yes, I can. Thank you.
Great. So there's a lot of questions coming in, and eventually we've had a hard time keeping up with them. So let me just pick some that were sort of heard a couple of times. One is, well, there were several questions about, is this function or that function in the CUDA accelerated group? Is it in the GPU? And I think you had a couple of slides back a link to basically the list. Maybe you could show and emphasize that a little bit.
Yes, so this particular web link is a great place to start. Is it okay if I were to show this link and its contents further? Julia?
Sorry, your audio cut out a little bit there.
Oh, okay. So yeah, so the best place to start on a comprehensive list of all the functions available on the GPU is this particular link. This is documentation that is maintained by itsy.com on their opencv.org website. So this would be the best place to start for any particular functions that anybody is looking for.
Okay. And then also in the vein of further information, there were some questions about, are there books about OpenCV and CUDA?
I think that would be a good question for Shervin.
Yeah, I don't know if his audio is on. He did send there is a link on the OpenCV website, opencv.org/books.html, that has got a list of books on it for OpenCV. For CUDA, there's a couple of books available. One in particular is called CUDA Application Design and Development by Ron Farber, and I guess we can put that in the notes. There's some other questions about sort of how do I extend the list of functions, write my own functions in CUDA. So Shalini, can you expand about that a little bit? I think you just had a bullet that said it was possible, but
Right. So like I mentioned, the OpenCV for CUDA module provides users with access to the image data. And in order to write your own custom functions, you do sort of need to understand have at least a high-level understanding of the OpenCV of the GPU architecture, the NVIDIA GPU architectures, as well as the CUDA the CUDA toolkit. So the best place to start for sort of understanding how to program in CUDA, I would recommend would be to go to the NVIDIA Developer Zone and to download the CUDA toolkit, and also it comes with a whole bunch of examples and detailed documentation about both the GPU architecture as well as good guides to get you started. The other good sources for learning CUDA, like I mentioned, are the courses, open source courses on Coursera and Udacity. The one offered on Udacity is actually by a senior research scientist here at NVIDIA and is very informative. So I would encourage you to go check those out. So the short answer is you do need to know CUDA in order to write your own functions.
okay. Another question here is about the Tegra optimizations, and the question is, does the OpenCV port on the Tegra platform exploit the ARM quad cores, or are the optimizations only GPU specific?
Right. So the Tegra optimizations, there's only a few functions that do use the quad core, but there are some functions that use the quad core. And an example of that is actually the HAR face detector that does use, so there's a few functions that are multi-threaded, but the bulk of the optimizations are using the Neon SIMD vector processor on the ARM CPU, and then there's a few other functions, for example warp and resize, that use GLES optimizations.
Thanks. And another question, maybe a couple of related questions about additional optimizations. So there's a question about if you call multiple GPU functions in a row, does the data have to go back and forth between the GPU, or is there some way to optimize that data flow? And another sort of optimization is, can you overlap CPU and GPU computation to run those in parallel using OpenCV?
Yeah, those are both very good questions. For the first question, you do not, if you are running a string of operations on the GPU one after the other without needing to run anything on the CPU, then you do not actually need to go back to the CPU every time. It's perfectly okay, and in fact in that example that I showed, we ran two functions on the GPU, the first of which was the bilateral filter and the second was the canny, and we ran both of them on the GPU, after which point we transferred the image back to the CPU. So it's perfectly okay to do that, and is a great optimization to save on the transfer times. With regards to the second question, which is whether we can overlap or timeshare the operations of transfers with the GPU, I believe it is possible. However, whether that functionality is available specifically in OpenCV, that's not something that I'm aware of. However, it is possible to do it in CUDA, but not sure if you can do that in OpenCV for CUDA.
Okay. I have another question about where'd it go? Oh, well, just in general about using the GPU versus using a multi-core CPU. What is the advantage of the GPU over the multi-core CPU?
Right. So the one advantage that comes to my mind is the fact that not many functions in OpenCV are actually ported over to use multi-core CPU. So if you look at the functions that use the TBB library, for example, they're much fewer. However, if you do have a powerful enough multi-core CPU, then and such that it's comparable in performance to your GPU configuration, then it might be the case that you might get similar performances for both of them. So one advantage is just the sheer functionality available. OpenCV for CUDA has about 250 functions, whereas the TBB enabled functions are far fewer, and yeah, so that's definitely there.
Okay, great. We have a question about Python. I guess we have Python programmers out there asking about Python support. I guess either, well, the question asks about NVIDIA support of Python, but are you aware of how the Python support is there for OpenCV?
Right. So the CPU version of the OpenCV, I understand, is for the most part supported with the Python bindings, and the code underneath actually runs at the C or C++ level. They're just the Python bindings are just bindings, like and pretty much like the Java as well. However, this might be a good question for Sherwin if he's looked at. I've actually never looked at whether there's Python bindings for the OpenCV for CUDA part. Did Sherwin have any input on that?
Yeah, I don't see any feedback from him there, but maybe you can type that into one of those questions. I guess I would also add that there is, not unrelated to OpenCV, but there is a version of Python, a compiled version of Python that is now available from a third party called Anaconda that actually supports Python code for the GPU. let's see, there's, I guess maybe now is a good time to remind people, because we're starting to get the questions about can we get copies of this webinar? Is it going to be available? Can we get the transcripts or recordings?
Okay, this is Donal again. I just want to jump in and thank Shalini and Frank and Shervin and Julia for putting together a great presentation this morning. And the answer is yes. It's probably one of our most common questions. Is the recording will be available. The PDF of the slides will be available for download on the GTC Express web page in about a week or so. And that URL is gputechconf.com/GTCExpress, which is right there actually on the screen. So I wanted to briefly mention a couple of things in closing. One is, as you can see on the slide there, we have a pretty full lineup of webinars in the next few weeks. We have got one tomorrow. It's a finance-related webinar, and then over the coming weeks we have cloud-related webinars and other developer tools-related webinars. So if any of those are appealing to you, please register on the GTC Express website. And again, URL is right there on the screen. And finally, I just wanted to mention that if you didn't get the opportunity to attend NVIDIA's GPU Technology Conference back in March, we have made available the almost 400 sessions. We've got them available for download, and we actually had about 15 or so sessions related to computer vision at GTC, and you can download those at gputechconf.com/on-demand and enjoy delving headlong into that great content. So that's it. We really appreciate you joining us today. I hope you can join us next time, and with that, take care and have a great day. Bye-bye.